All this while, I've been developing the notion of energy. My initial claim was that there's a number that you can calculate that has a remarkable property, that it never changes or changes predictably no matter what occurs. That's a powerful thing. And over the past few discussions, I've been developing that idea. This is a really special discussion today because I'm going to solidify that idea and from it create probably the most important physical law of our universe that there is. So some careful thinking, please. Along the way, I've devised 3 different forms of energy. In my universe, there are many more than 3. But just as I have restricted the number of forces that we consider in our honors physics, I have similarly restricted the number of energies that we'll consider. But it's okay. With these 3, we'll be able to solve some rather remarkable problems. Very, very sophisticated. More interesting problems than we've ever been able to solve before. And that makes it worth doing. And so here they are, these 3 energies. First is the kinetic energy, the energy of motion. If an object has a speed, then it has a kinetic energy. It's easy to calculate. 1/2 mv squared. It's not a vector. It doesn't have components. It's 1/2 mv squared. So that's kilogram meters squared per second squared. And that's a joule, which is our SI unit of energy. If I want to ask myself, does an object have kinetic energy? It's as simple as asking myself, is it moving? And calculating that kinetic energy is just as simple. Kinetic energy, the energy of motion. The next 2 energies on my list are energies of position. Energies of position are known as potential energy because this form of energy has the potential to manifest itself as kinetic energy again. And that's all wrapped up in the specialness of the number. The first is the gravitational potential energy, mgh. Again, easy to calculate. Again, measured in joules. There is a caveat, however. How shall I measure the height h of an object for the purpose of calculating its gravitational potential energy? My recommendation for your problem solving is that you always choose h to be the lowest energy configuration, the lowest height in the system. That way, the gravitational potential energy will always be positive. Because it's possible in a coordinate system to have a negative height, it's possible to have a negative gravitational potential energy, but I don't like negative numbers running around inside my calculation if I can help it. So I'll always choose the lowest height to be 0, and once I choose it, the gravitational potential energy is easily calculated, mgh, mgh, mgh. It seems arbitrary, but really, it doesn't particularly matter what the gravitational potential energy is. What matters is by how much the gravitational potential energy changes. The third energy on my list is the spring energy, 1/2 kx squared. Easy to calculate, where x is the compression or the stretch of a spring in meters. The constant k that appears is the spring constant. It determines the stiffness of the spring. A large spring constant in newtons per meter means a spring that is very stiff, difficult to stretch or compress. A spring with a low spring constant is very light, easy to stretch or compress. 3 energies, easy to calculate, which is what I promised they would be. But which one of them is the special number? Which one is the one that matters? Which is the one that has the useful property? Well, it turns out all of them. Because now, since I've developed these, I can define capital E, the total mechanical energy. Capital E is the total mechanical energy. And it's as easy as it sounds. That mechanical bit in there is just in there because I don't have any electrical energy, I don't have any nuclear energy, any chemical energy, because we're not considering them in our physics course. This version of it just contains forms of mechanical energy, but that's okay. If you want to add in other forms of energy, go ahead and add them in. The total energy is as easy as it sounds. The total mechanical energy is the sum total of all of the forms of energy that I have. Now, in our case, we have 3. This equation could be more elaborate in a chemistry problem, in a biology problem, in an engineering problem, in an agricultural problem. But in our case, it has 3. The total mechanical energy, easy to calculate. You just add up all 3 forms of energy, and all 3 forms of energy individually, easy to calculate. Maybe a little bit of labor, using your calculator quite a bit to get them, but the total mechanical energy, easy to calculate. The total mechanical energy is the special number. It's made of lesser special numbers. But this total mechanical energy is the symmetry of the universe that I refer to. Well, it's one of a family of symmetries of the universe, sameness of the universe. This number that you can calculate in joules, the total mechanical energy, has the marvelous property that it never changes or changes predictably no matter what happens. No matter how sophisticated, no matter how complicated, no matter how mysterious or unknown, this quantity that has the that is known as the energy is fundamental in our universe. I'm now going to use it and put it to great practical purpose. Recall the work-energy theorem. The work done is equal to the change in the kinetic energy. On the left-hand side of the equation, I have the work, which explicitly means the work done by all forces that do work in a given physical situation. Just like when I apply Newton's second law on the left-hand side, it says sigma F, the sum of all forces. In any given physical situation, there could be a lot of work being done because there could be a lot of forces doing work. On the left-hand side of the work-energy theorem, W is the sum total of all work. But what I realized along the way is that work done by forces now can be divided into two classes. The work that is done by ordinary, everyday forces, the work that is done by non-special forces, and the work that is done by conservative forces. So on the left-hand side, I'm just going to separate them like this. The work can be divided into two classes. Work done by ordinary forces and work done by conservative forces. Let me refresh you. The conservative forces in our course are springs and gravity. All other forces are non-conservative. In our course, it's just springs and gravity. And the reason why is that springs and gravity are special. The gravitational work depends only on where you start and where you finish, the initial height and the final height, and it doesn't depend on how you get there, and that makes the gravitational work special. And so we don't think of it as work at all. We think of it as gravitational potential energy. The spring potential energy depends on how far the spring is stretched to start and to finish, and it doesn't matter what happens in between. And so we don't think of it as spring work, we think of it as the spring potential energy. So the work can be divided into two classes, the work done by non-conservative forces and the work done by conservative forces. The conservative force work is related to potential energy this way. The work done by conservative forces is equal to the negative of the change of the potential energy. Now, that's a bit sophisticated. The reason why I'm saying that is I realized, particularly when I was developing the gravitational potential energy, I realized that when I raise an object up, I increase its gravitational potential energy. Positive change in gravitational potential energy. But when I do that, the work done by gravity is negative, because the force of gravity is downward and the displacement is upward, so gravity's doing negative work, but the potential energy is increasing, which means the sign of the work is opposite the sign of the change in potential energy, and that's what this equation means. Well, now I make a substitution in something very lovely. Substituting this work done by conservative forces into my work-energy theorem, I now have the work done by non-conservative forces minus the change in the potential energy. What potential energy? All potential energy. Spring potential energy, gravitational potential energy, whatever potential energies you have on hand, is equal to the change in the kinetic energy. So I've taken this equation and I've made it into, well, look at that negative change in potential energy there. I can't help but want to move that to the other side of the equation so that the work done is equal to the change in kinetic energy plus the change in potential energy. So all of the work done by gravity and all of the work done by springs has moved over to the right-hand side of the equation to live the rest of its life as potential energy. And what's left on the left-hand side is work done by non-conservative forces. Now, the change in the kinetic energy, delta K, plus the change in potential energy, delta U, gives me the change in both kinds of energy. When I add them together, the work then is equal to the change in the total mechanical energy. The work done by non-conservative forces is equal to the change in the total energy. Now, I haven't invented any new physics here. The work-energy theorem, work is equal to delta K, perfectly happy with that. Can solve every problem with it. But this equation that I've written now is a more powerful idea. here on the left-hand side of the equation is the work done by non-conservative forces. If no work is done by non-conservative forces, then the change in energy is zero. If there's no work done by non-conservative forces, then the energy does not change. When a quantity doesn't change, we call it conserved. That's why they're called non-conservative forces. Because when non-conservative forces do work, they can increase the energy doing positive work or decrease the energy doing negative work. Non-conservative forces change the energy, and in their absence, the energy is conserved. When gravity does work and when springs do work, they conserve the energy. When gravity does work, it doesn't change the total energy. When springs do work, it doesn't change the total energy. That is why gravity is a conservative force. When I first said that gravity was a conservative force, it really didn't make a lot of sense. And now it makes, in this context, complete sense. When the force of a spring does work, it doesn't change the energy. That's why the spring force is a conservative force. Now, this change quantity, the change in energy that appears here on the right-hand side, like any other change quantity, is the final energy minus the initial energy. Final minus initial. All change quantities work that way. And so now I'm ready to write this equation in its final form. I'm going to add the initial energy over here to the left-hand side. And I'm going to write that the initial energy plus or minus the work is equal to the final energy. The law of conservation of energy. A fundamental law of the universe that, so far as we can tell, applies to everything that has ever happened or ever will. It applies in every context to every physical transformation that takes place in our universe. It's really quite spectacular. And when you read it from left to right, it reads exactly like my definition of energy. What energy is. Energy is a number that you can calculate. Of course it is. Because it's this plus this plus this. Kinetic energy plus gravitational potential energy plus spring energy, and they're easy to calculate. I calculate them, I add them together, I have a number of joules. That is that number. Energy is a number that you can calculate, that never changes. If there's no non-conservative work, my equation states that the initial energy is equal to the final energy. The energy never changes. Or changes predictably. If there's some force that adds energy in, then I can predict how much and add that much energy in. Or if I have a force that removes energy from the system, I can predict how much and remove that energy from the system. Energy is a number that you can calculate that has the remarkable property that it never changes or changes predictably no matter what occurs, no matter what strangeness happens between the beginning and the end. Energy is a special number. When a thing goes from the beginning to the end, the speeds change, the positions change, the accelerations change. And not in our physics, but also the masses might change. The thing that remains unchanged is the energy, the law of conservation of energy. Naturally, what I would like to do is use this new law of conservation of energy to solve problems. And I can solve any problem. I can solve the problems in academic physics, and I can solve the problems going on in the most advanced physics laboratory in the world. All of them. So I begin with this one. Here I've drawn scenario where I have a block here at position A. It's up here on the top of a slope. I'm going to let it go, and I'm going to let it run down the slope. Notice the slope is curved. The slope being curved means the acceleration will not be constant, which means kinematics are out of the question. Maybe I could use Newton's second law, but the acceleration is not constant. I don't know how to do calculus, and so I can't solve it that way. So already I'm in trouble with this problem. It's more sophisticated than problems I've solved in the past. So it slides down here frictionlessly until it arrives at position B here, where all of a sudden the surface upon which it slides becomes rough. I know what's going to happen. I've already solved a bunch of physics problems. The frictive force is going to slow the block as it travels. From position B to the end of the friction-y bit here, it's going to lose some speed as a result. And then it slides over here and it rams into this sort of plunger thing here with a spring attached. Now initially the spring is relaxed. It's not stretched, not compressed at all. But when the block hits it, the spring will begin to compress. The spring will exert a force opposing the motion of the block, and the block will come to rest. That's the point that I'm interested in. The question that I would like to answer in this problem is how far will this spring be compressed when the block hits it? And I'm going to solve it using the law of conservation of energy. I'm not going to solve it straight away. I'm going to mess around and find some extra stuff and do a bunch of explanation. Because the law of conservation of energy is so very fundamental, the solution to this problem is actually extraordinarily simple. But in order to solve it, I'm going to need some numbers. So let me define something. I'm going to say that the mass of this object here is equal to 2 kilograms, and that its height above zero, and you'll notice that I choose the zero height here to be the lowest possible height that the mass will have. Again, this assures me that my gravitational potential energy will always be positive. So it has a height above zero. I'm going to call it 0.5 meters. It's half a meter above the lowest point of the system. This frictional distance here, where the force of friction acts, is going to be, according to me, 0.5 meters. Just a half a meter of surface that is rough. The rest of the surface, everywhere else, is frictionless, except for this bit. There's a rough patch. Since it's a rough patch, I'm going to need a coefficient of friction. I'm going to set the coefficient of friction to be 0.2. And then I encounter this spring. A spring has a stiffness constant, K, that describes how much force I get per unit meter of stretch or compression. I'm going to say, for the purposes of this calculation, that the spring constant of this spring is 80 newtons per meter. And now I have all the information that I need to calculate how far the spring compresses in bringing the block to rest. To do so, I'm going to use the law of conservation of energy, that the initial energy plus or minus any work that is done by non-conservative forces is equal to the final energy. The law of conservation applies every time and everywhere in this process. I can easily calculate the total amount of energy at position A. I can easily calculate the total energy at position B. And I can easily calculate the total energy at position C. And the work energy, or the law of conservation of energy, relates them for me. So before I actually chase down my final answer, I'm going to begin by asking an initial question that's not really necessary for me to get the answer. I could go right for the answer, but I'm going to do a few more things first. I'm interested in what is the speed of the block when it reaches position B, because I've realized that I can't use kinematics and I can't use Newton's second law because I don't know calculus, and I don't know, even if I knew calculus, I need to know the actual mathematical shape of the incline, and I don't, just a curved sort of ramp. I want to know, what is the speed at B? I've never been able to solve it before. The law of conservation of energy is going to make it easy for me to do that, because the energy that the object has at A, plus or minus any non-conservative work that is done, must be equal to the energy that it has at B. And examine the behavior between A and B. This block slides down a frictionless ramp on its way to B. There is no work done by friction, because there is no friction. There's no normal, well, there is a normal force, but the normal force is perpendicular to the displacement the entire time. So how much work does the normal force do? None, because perpendicular forces do no work. Which means, on its way to A to B, or on its way from A to B, the work done by non-conservative forces happens to be zero. The work done by non-conservative forces happens to be zero, and this implies that the energy at A is equal to the energy at B. So let me calculate how much energy there is at A. Calculating how much energy there is at any particular stage or point in a problem is often tricky for students, even though it's quite simple to do. All you have to do is follow this sort of recipe, strategy. Look at position A. There's the object. Its velocity is zero, just sitting there, and it gets released and then it goes away. But right there at A, what is its total energy? Well, its total energy is what the total energy always is, the sum total of every kind of energy that it can have. Look at my list. Kinetic energy, 1/2 mv squared. Does the object at A have kinetic energy? No, because it doesn't have a speed. It's not moving. Now, sometimes you say, well, I didn't know it doesn't have energy at A, but because it's not moving, but it will be. I'm not talking about what happens later. I'm talking about at A. No velocity, no speed, no kinetic energy. The kinetic energy is zero. Is it high? That is, does it have a height above zero? Yes. So therefore, it has gravitational potential energy, and that gravitational potential energy is mg times the height at A. Is there a spring in the problem? Yes, but the mass at A is all the way over here. It hasn't even encountered the spring yet. The spring is sitting there relaxed, not stretched, not compressed, no energy. So it turns out at A, the total mechanical energy is the sum of the kinetic energy, gravitational potential energy, spring energy. But that's just the gravitational potential energy, because the kinetic energy, the spring potential energy, are zero. And easy to calculate based on the numbers that I've chosen, because I chose the mass to be equal to 2 kilograms. And I'm going to, and for the simplicity of my problem, I'm going to use g, the acceleration due to gravity, just to make things easy on myself. I'm going to use 10 meters per second squared as the acceleration due to gravity. Though I'm going to get approximate answers, but it makes it easy for me to do the math. So the mass of 2 kilograms multiplied by the acceleration due to gravity, which is 10 meters per second squared, multiplied by the height, which is 0.5, gives me 10 joules of energy. 10 joules of energy. But Shally, what does that mean? It has 10 joules. What does it mean? It means there's a number that you can calculate, and that number happens to be 10. No, but what is energy? I don't know. Energy is a symmetry of the universe. It has a remarkable property that I'm going to take advantage of. It just so happens that in this configuration there are 10 joules of energy. I've calculated, and it was easy. It has 10 joules of energy at A, and since no energy is added or removed, when it gets to B, it still has 10 joules of energy. But the energy has changed form. It's no longer gravitational potential energy, because when I get to B, the height is now 0, and there is no gravitational potential energy. The spring energy is 0, because I haven't even reached the spring yet. But at B, it is moving. So when it gets to B, the energy at B is kinetic energy, 1/2 m VB squared. I call it VB because the velocity is different elsewhere in this whole motion. Something really specific. I'm talking about the speed at B. Well, if the energy at A is equal to the energy at B, then 1/2 mv squared here is equal to 10 joules of energy. And so I can calculate what the speed at B is. The mass is 2 kilograms, and I got 1/2 the mass, so the 1/2 cancels the 2 kilograms of mass. So VB squared is equal to 10, which means that VB is equal to the square root of 10, which is about 3.2. 3.2 meters per second is the velocity at B, which I could not find using kinematics, could not find using Newton's second law, and could find using the law of conservation of energy. But that's not what I was after. I was after the compression of the spring. So I'll start again. This time, instead of comparing the energy at A to the energy at B, I'm going to compare the energy at A, which I already know is 10 joules, so it's convenient to do that. I'm going to compare the energy at A to the energy at C, and hope that that leverages me an advantage to solve for X. Naturally, it will. The energy at A is equal to 10 joules, that's fine. Plus or minus any work done. Oh, Shally, that's 0. No, it's not, because in order to get from A to C, the block has to slide over the rough patch, where there's a normal force. But that normal force does no work, but where there's friction. And the friction force does work, because the object is displacing to the right, and the friction force is exerted to the left. The work done by the friction is negative. The work done by the friction is negative. Friction is going to remove energy. Friction is going to remove energy from the motion. So I want to calculate how much work is done by friction. Well, the work done by friction is going to be equal to negative the force of friction multiplied by the displacement. We've done enough physics so far that I think you know that the friction force in this case, which is mu times the normal force, is mu mg, because the normal force will be equal to mg on a horizontal surface. So the friction force is mu mg multiplied by delta x. This is the work done by friction, and because of the numbers I've chosen, easily calculated. The coefficient of friction is 0.2. The mass is 2. G, I'm using 10 in approximation. And delta x is 0.5. So it's 0.2 times 2 times 10 times 0.5 is negative 2 joules of work. Which means as the block slides across the frictional part, 2 joules of energy are removed. I know that you're capable of this. There were 10 joules. Friction removed 2 2 joules, I'm left with 8 joules of energy. Do you see how simple conservation of energy is? I had 10, I removed 2, and so I'm left with 8 joules of energy. Where did that energy go? Well, what happens is when the block slides across the frictional surface, it gets warm. Where did the energy go? That 2 joules of energy became thermal energy, and it drifts away into the room and out the window, removed from the system. Very often when we remove thermal energy from a system, very often we call that Q, the thermal energy removed. Friction creates thermal energy. That's how it removes the energy from the system. And that thermal energy is associated with the vibration of molecules. We don't need to get into those details. But what I've learned here is that the energy at C is equal to the energy at A, which was 10 joules, minus the work done by friction, removing energy by doing negative work. And so I discovered that at C, I have 8 joules of energy left over. Now let's investigate the energy at C. Look at it. What I've described in my problem statement is that the block hits the spring and the spring compresses until at C, the spring has arrested the motion of the block and the block comes to rest. What is the energy at C? Well, it's the total mechanical energy. It's the sum of all the energies that it can possibly have. Let's go back to the list. Kinetic energy, 1/2 mv squared. Does it have kinetic energy? No! I've explicitly stated that the spring is going to stop the block from moving. When it's not moving, it has no kinetic energy. Does it have gravitational potential energy? No, because when it's at the position C, its height is 0. It has no gravitational potential energy. Does it have spring energy? Yes. Finally, spring energy comes into the problem because the spring has been compressed. And so, this 8 joules of energy is equal to the energy at C, which is spring energy exclusively. So 1/2 K x squared is equal to 8. I know the spring constant is 80. I know the spring constant is 80. So x is going to be equal to, the spring constant is 80, half of 80 is 40. X squared is going to be equal to 8 divided by 40. And so x, the compression of the spring, is going to be 0.45 meters. Yeah? 0.45 meters. Or, if you like, 45 centimeters. A problem that I could not solve with kinematics or Newton's second law, resolved quite simply by the human observation that our universe has rules. And those rules are the manifestations of aspects of the universe that do not change. That energy is a number that you can calculate, that has the remarkable property that it never changes or changes predictably, no matter what occurs.